In this video, we're going to look at the mechanism of the Claisen condensation. Here I have a simple ester and some ethoxide. What's the ethoxide going to do? Well, it could attack the carbonyl, kick out the ethoxide, but that's kind of redundant. Let's do something more interesting. Let's form an enolate. Now the esters are not very acidic, but some small amount of enolate would indeed form. So let's draw that out. Grab the proton, form a carbon-carbon double bond, push the electrons out onto the carbonyl, and push the magic arrow, and we have our enolate. Now, what can this enolate react with? Well, it can, of course, grab the proton from the ethanol and go backwards, and probably it does. But more interestingly, it can do a reaction with another mole of the starting material. So let me bring a copy of the ester over here, and let's do a reaction here. What can that ester do? Or what can that enolate do? It can attack the ester, reform the carbonyl, double bond comes down and attacks the carbonyl over here, putting the negative charge on that carbonyl. So we draw this one out. We get this tetrahedral intermediate. Now, when this tetrahedral intermediate falls apart, it looks at this and says, what's the best leaving group? Well, in this case, the best leaving group is the ethoxide here. So let's kick out that ethoxide. So we'll bring the negative charge back, forming the carbonyl, and we'll kick out the alkoxide. And what do we get? We get this product right here, which is indeed a nice stable product, but of course, and this thing is has a very acidic proton. So we're not done, because if this ethoxide could have formed an enolate up there, it certainly can form an enolate down here. So there's one more step where we use another mole of ethoxide. Well, actually, I don't need another mole. I've already got them. I already have an ethoxide there. So let me just draw in the hydrogen. The ethoxide comes around, grabs that proton, and forms a double bond there, pushing the electrons out onto the ester oxygen, or the ketone oxygen, and there's our favorite final product. Now, this guy here is a very stable species, and indeed, the formation of this nice delocalized enolate is the driving force for this entire reaction. If we didn't have that ionizable proton, this reaction actually wouldn't go, because it turns out that without this step, this reaction has an alternative. Instead of kicking out the ethoxide, it would just undo the Claisen reaction. And so, in fact, these things are all in equilibrium, and the whole driving force is for the most stable species. And in base, this is only forms a very weak enolate. If we can go all the way down here to this deep hole of this delocalized enolate, that'll be the most stable species. But in the absence of that, the equilibrium will just shift back to the esters. So the key thing on the Claisen condensation is that you have to be able to form this delocalized enolate when you're done with the process. Now, once you have this, you can protonate it, and you'll have a beta keto ester, which you could decarboxylate if you like. You could hydrolyze and decarboxylate, or you could use it for some other reaction. Indeed, you could use this enolate here for some other reaction, like an alkylation. So let's just reverse a little bit, and let me reload and start all over again. And let's just think of the situation if we had the methyl there. Now there's still a hydrogen, okay, and so we can still write our initial step. We can go like this. We can form our enolate. Here's our enolate, okay. And that enolate could indeed react with another mole of the starting material. Okay. Draw it out. Coming back. Chelate comes around, attacks the carbonyl, and we get this product here. Okay, and again we can I can kick out that ethoxide. And we can go to this species, but now this, you see, is where we're stuck. That ionizable hydrogen between the two carbonyls, well, there ain't one. So we can't go on and form a stable enolate. So this reaction actually will reverse, and it'll just go backwards, and this one will just go backwards, and this one will just go backwards. Whoops, those aren't arrows. Sorry. And this will go backwards, and this will go backwards, and we'll end up where we started from. So mechanistically, this thing can only go forward if there's an ionizable hydrogen at this point. And of course, if there's a methyl there, we're going to steal one hydrogen for the first step. There'll be no second hydrogen for down here. So Claisen condensation only works if there are two hydrogens next to the carbonyl, or actually three. I mean, there has to be at least two. You could do it with ethyl acetate. So if you only have one hydrogen, the reaction is not going to work. Otherwise, the mechanism is pretty straightforward, and you always basically do the same things.